So in these summation problems, going from 1 to a certain number, one way is we could literally just use our calculator and add this. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 28, 36, 45, 55. So I could literally just add those numbers. It would be tedious, but possible. The problem is it just becomes more and more complex as the numbers get longer and longer. So we have to think about, well, what could we do? Well, if you start to play around, what you may notice is if I take the first and last number and pair them, in this case I get 26. And then if I do that with the next set of numbers, I get 26. And if I keep doing this over and over again, I'll get 26. And so I can see that if I pair them all up, make this nice and big, I can keep going, and every time I'm getting 26. Alright, so if I look here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 groups of 26 plus the 13. So I can actually multiply that out and do 12 times 26 plus 13 to get exactly what this sum is. And if I multiply and add these numbers together, I will get to 325. So then we get to the third problem about trying to add the numbers 1 to 100. Now that is much harder to do that same type of pattern here of lining up and matching. So instead, let's go back and see if we notice any patterns. Well, the two parts that matter is that we have this number of 13 and we have this number of 26. And we think about, well, what's the relationship between 26 and 13? Well, we know that 13 is half of 26. So let's think about a couple things here. So maybe we could say that 13, I'm going to extend my page a little bit, that's the same as 26 over 2. Now, if we go back here and say multiply this, and we think about, well, how many numbers were used to make these 12 pairs? It took 24 numbers to pair up. So that's the same thing as saying 24 pairs, and we have that 26, so 24 over 2 because we have the pairs. Now if we think then, okay, let's add these together, this would be the same as 25 times 26, because if you think about this as like 1 times 6, I can, and it's a distributive property. And if I do 25 times 26 divided by 2, I'll get 325. And if I notice, well, how does that relate? Well, that is the last term and the term that follows. And that gives me 325. So it appears that what I could do, and I could try this with smaller sets and larger sets, is that I can, if it's the sum of 1 to some number and it's consecutive, I can take the last term times the term after it and divide by 2. So if I did that with 100, that would be 100 times 101 divided by 2. And if I did this, I would get 5,050. And I could actually use something like Excel or some other program to double check that the summation of 1 to 100 is 5,050. But what we eventually will learn is that the sum will equal, we'll say n is the final term times n plus 1 divided by 2. And this will work for any of the sums. So then the question was the alternative view. Well, how does this play into effect with what's going on? So if I look at this, what I have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, and 4, 5, 6, 7, 8, 9, 10, 11 columns. So if my entire shape was filled in, I would have a 10 by 11 number of shaded blocks. But if I look at this, well, how many of those are shaded in? And look, that's the consecutive numbers, 1 through 10. If I counted the blocks, 1 in the first one, 2, 3, 4, 5. What I notice is half of this rectangle is shaded in. So it goes back to that original problem of, well, how many do I have? I have 55 because it's half of the rectangle. So it's another way you can help students think about this visually as well as doing it with the numbers numerically.